In this segment, we're going to look at some examples of drawing Newman structures, and we're going to learn such things as how to convert Newman structures into IUPAC names, and how to convert IUPAC names into Newman structures, and how to draw some of the specific energy conformations for a variety of different Newman structures. So getting started with this, there are about 4 example problems in this segment that we're going to look at, and the first of these example problems is the one I'm showing here. So for the following molecule, what we're going to do is provide the IUPAC name of the molecule that's shown below as a Newman projection. And we're going to ask the question of whether this structure that we've drawn here is the lowest energy conformer. And if not, let's redraw it as the lowest energy conformer. So first off, we need to provide the IUPAC name for the molecule that is listed here. So in order to list the IUPAC name of a particular molecule, rather than going straight from the Newman projection and trying to come up with a name based on the Newman projection itself, what I highly recommend as the strategy for tackling questions like this is to instead redraw this molecule as either a line angle formula or a condensed structural formula or Lewis structure in order to name it. Because looking at just the Newman projection, it's really hard, even if you have a lot of experience with organic chemistry, to come up with a name directly from there. It's much easier if you redraw it as a more manageable molecular structure, which we recognize how to find the longest carbon chain in and things like that. So let's go ahead and we're going to redraw this as a Lewis structure or as a condensed structural formula, whatever your favorite type of structure is. So to get started here, what I'm going to do is go ahead and I'm going to change the color of the atoms that are in front. Remember that center where the 3 lines intersect in that upside down Y shape represents the first carbon of the frame of reference of our molecule. And the lines coming from that represent which atoms and groups that carbon, the first one of the frame of reference in the center there, is directly bonded to. So the carbon that's in our frame of reference is directly bonded to a CH2CH3, and it's directly bonded to this isopropyl group shown in the lower right-hand side. That doesn't mean that the name isopropyl is going to appear in the IUPAC name for this molecule. We're just saying that that's what we see right now. Once we draw out the full molecule, we're going to use our IUPAC rules to come up with the rigorous name of the molecule. So first off, in order to draw the structure as a condensed structural formula or a line angle formula, what we're going to do is I'm going to start by putting in the carbon that is the first carbon of our frame of reference, and I'm going to put a star on it to indicate that that's the first carbon of the frame of reference. That's the carbon that's appearing at the center of our Newman projection. And then we need to draw out what groups are directly bonded to that. So directly bonded to that, we have the hydrogen, CH2CH3, and the isopropyl groups. We're going to go ahead and plug those in. You can plug those in wherever you like here. And I'm going to try to do this in a way that will make a chain that looks somewhat logical. So I'm going to do CH3, CH2. The main thing is that those 3 groups have to be directly bonded to that carbon that we've put a star on. That is the carbon that I'm also highlighting right here. That's the first carbon of the frame of reference. So that's that carbon that's right in the center there. Okay, so that carbon is directly bonded to CH3, CH2. It's directly bonded to a hydrogen. So I'm going to plug in that hydrogen. And then it is also directly bonded to that isopropyl group, CH, CH3, 2. So I'm going to go ahead and plug that in, and in order to do that, I'm going to show that coming off as a branch. So I'm going to show CH, and then I'm actually going to show the 2 bonds coming to the 2 methyl groups explicitly, because by drawing it out like that, that'll help us see where the longest carbon chain is in this molecule. So now at this point, what I've accounted for in the structure that I've drawn is I've accounted for the CH3CH2 group up here. I've accounted for that being bonded to the carbon that is in the center, the first carbon of the frame of reference. And then I've accounted for the fact that that carbon that's in the center as the first frame of reference is directly bonded to an ethyl group. That's shown right here. And it's directly bonded to a hydrogen atom. Additionally, as we continue down the chain here, to the right of this, I'm going to put the carbon atom that is the second carbon of the frame of reference. And I'm going to put that in blue here. So that circle in the back represents the carbon that is immediately directly connected to the carbon that was in front in our Newman projection. That CH carbon that we've highlighted in yellow is directly bonded to the carbon that's behind it and that's circled. So I'm going to put C, and then I'm going to put a little circle here to emphasize that that is the carbon represented by a circle in back. And then we look at what lines end at the outside of that circle. We plug those in blue, and that's going to show us what groups are directly bonded to that carbon. So that carbon, the second carbon of our frame of reference, is directly bonded to a methyl group, directly bonded to a hydrogen, and directly bonded to another hydrogen. So what I'm going to do here then, to show that it's directly bonded to two hydrogens and to a CH3 group, is I'm going to show that carbon having H2 directly bonded to it. That would be the two hydrogen atoms here and here. We know those are directly bonded to that carbon and back because these lines are the ones that end at the outside of the circle. And then that carbon is also directly bonded to a CH3 group. That's the CH3 group I'm putting in blue here. So I'm going to go ahead and show the CH3 group right now. And that means that both those two hydrogens and the CH3 group are what are bonded to that carbon in blue. So now we have drawn out a structure that looks much more manageable, like a condensed structural formula, and we can go about coming up with the IUPAC name for that molecule rather than directly trying to come up with a name from the Newman projection, which is really a pretty cumbersome thing to do and not something I would advise. So let's come up with a name for this using the IUPAC rules, and if you need to go back and review the IUPAC rules, that was back in the lecture on naming of alkanes. So we're going to name this alkane by, first off, find the longest carbon chain. So we're going to look for the longest carbon chain in this molecule. And as we look for that longest carbon chain, what I see in looking at this is that the longest carbon chain has a total of 5 carbons. And there's a couple of different ways that we can look at the longest carbon chain. One of those possibilities is that the longest carbon chain could be the chain that runs right through here. So that 5 carbon chain there. Another possibility that I'm going to highlight in blue is that the 5 carbon chain could go through here in blue. And when you get to this point, it doesn't matter if you turn left or right because those two groups are symmetrical. They're both CH2, CH3, so I'm going to take a right there. And that would also allow you to map out 5 carbons in that chain. So which of these is going to be the right way to number and name this chain? The correct way is going to be the way that gives more branches. So in the case of the gray highlighting line that we drew there at the bottom, that chain would only have 1 branch coming off of it. That is inferior to a chain that has more branches coming off of it. So the blue highlighting that we did gives us a 5 carbon chain that has 2 branches coming off of it. 2 branches, certainly better than 1. So we're going to go with the blue highlighting route as our way of going about picking out the longest carbon chain there. And remember, when you pick out the longest carbon chain, you want to start numbering that carbon chain from the end closer to where a branch comes off. And so if we start numbering from up here, with that being carbon 1, 2, 3, 4, 5, that's going to allow us to put a branch, that methyl branch, at carbon number 2. Whereas if we numbered from the other end of the chain, our first branch would not end up being until carbon number 3. So let's go ahead and we will fill in the parent name for this as pentane, because it's a 5 carbon chain. That ane suffix always indicates just that this is an alkane. And then we need to identify the branches coming off that. The branches are our methyl branch, which comes off at carbon number 2, which I'm highlighting in green there. And our ethyl branch, CH2, CH3, coming off at carbon number 3. We alphabetize those in the name. So ethyl comes before methyl, and so this is going to be 3-ethyl 2-methyl pentane. And remember that this is all one word with dashes used to separate the letters from the numbers. So methyl pentane all runs together as one word there. And we just have our dashes sprinkled in every time we're trying to separate a number from a letter. So that's going to be our IUPAC name for this particular molecule. Let's now do another example to, or fill in the last of this example rather, to ask the question of, is this the lowest energy conformer here in part B? If not, draw the lowest energy conformer. So we're looking to look at conformers. We're always looking at these Newman projections as our way of identifying whether this is the lowest energy conformer or not. And remember that by definition, the lowest energy conformer has to have the bulkiest group that's bonded to the carbon in front separated by a dihedral angle of 180 degrees from the bulkiest group that's bonded to the carbon in back. So lowest energy conformer, by definition, regardless of whether we're looking at this problem or others, means that there's a 180 degree dihedral angle, which I'm going to abbreviate as theta, that separates the bulkiest group that's bonded to the carbon in front of our frame of reference from the one that's bonded, the bulkiest one bonded in back. So 180 degree theta, dihedral angle separates the bulkiest group in front from the one in back. So to determine whether this is the lowest energy conformer or not, what we need to do is look at our carbon that's the first one in the front within our frame of reference, pick out which of those groups is the bulkiest there, and then determine where the bulkiest group is in back and what the angle separating those is. So looking at the carbon atom that's the center of our frame of reference in front, remember that the carbon in front is the one that is the intersection of those three lines of the upside down Y shape. And we can look at the three groups that are bonded to that. All of those are highlighted in yellow in our original Newman projection. And we see there we have an ethyl group, an isopropyl group, and a hydrogen. Think about which one of those is most bulky. What's going to make a group bulky is having the largest number of atoms and having the largest number of branches. And so comparing an ethyl group to an isopropyl group, definitely the isopropyl group is larger because not only does it have more atoms, it also has more branches. So I'm going to put a circle on that group as the largest, bulkiest group that is bonded to the carbon in front. Then we take a look at the carbon in back. That's the carbon that's circled in blue there. And we ask which of those three groups is the bulkiest. Looking at those three groups, the bulkiest one, we just have two hydrogens in the methyl group. Methyl is certainly bigger than either of those two hydrogens. So looking at these two, we would say that those two groups are gouged to one another, meaning they're separated by a dihedral angle of 60 degrees, rather than being anti, meaning they're separated by a dihedral angle of 180 degrees and making them the lowest energy conformer. So we need to draw this as the lowest energy conformer here as part B of this problem. So what we're going to do to draw that lowest energy conformer is we're going to rotate one of those groups, either the groups shown in blue or the groups shown in yellow, in order to place the methyl group and the isopropyl group 180 degrees apart. So in order to do this, what we can do is we will fix one of the two sets of groups, meaning either the groups in yellow or the groups in blue. So those are the sets of groups that are bonded to one of the two carbons of the frame of reference. We're going to set those stationary and rotate the other one much like you would rotate the propeller of a plane, going clockwise or counterclockwise, whichever one, it doesn't matter. So I'm going to choose arbitrarily to rotate the yellow bonds that are in front there and leave the blue bonds in back stationary to draw out this lowest energy conformer. So I'm redrawing just in blue the bonds that were in back. I'm trying to redraw those as identical as they were in the original structure. So I'm putting all the groups in the same exact place, CH3, H, and H. And then what I'm going to go ahead and do is draw in the atoms in front. And I'm going to show these in black rather than yellow because I think the black's a little easier to point out. We still definitely need the bonds to be staggered because by definition the lowest energy conformation has to be some staggered conformation. So I'm going to go ahead and fill in a staggered template there. And then what I'm going to do to fill in the lowest energy conformation of that is that I'm going to take and imagine that we're rotating each of these groups around by 120 degrees. So we're moving each of those, much like if you had the propeller of a plane and you were spinning that propeller of the plane around. When you move one group 120 degrees, you have to move the other one 120 degrees in the same direction. So we're moving each group 120 degrees clockwise in this case. We could have also started rotating them counterclockwise instead. As long as we're consistent about which direction we move, all is well. So we took our hydrogen, move it 120 degrees, it's going to come up to the top position. CH2, CH3 that was at the 12 o'clock position to start with is now going to move over here to our 4 o'clock position. And then our isopropyl group, our CH, CH32 group is going to be over here. And now to ask ourselves whether we have actually drawn the lowest energy conformation, what we need to confirm is that the highest molecular weight size group that's bonded to the carbon in back, that's our methyl group, is 180 degrees for the bulkiest group bonded to the carbon in front, so that'd be the bulkiest group in black, which I'm highlighting now in yellow here. So those are 180 degrees apart, and therefore this is the lowest energy conformation, and we finished off this problem. So we'll go on to the next problem now, which the next problem is going to give you some experience at working these types of problems on your own. So we're going to take a look at this molecule. The question being asked here is similar to in the last example, and if you hit the pause button right now and try to work through this problem, that will give you a good idea of whether you're able to rock and roll on these problems on your own. So hit the pause button, take a look at this problem, and then hit play again to go ahead and get the solution to this. For the solution, we're going to provide the IUPAC name first off. So to provide the IUPAC name, what I'm going to do is redraw this molecule as a line angle formula or as a condensed structural formula. And in order to make my life a little bit easier for purposes of that, I'm just color coding the atoms. You're welcome to color code the atoms using a highlighter or bringing colored pens and pencils to exams and things like that. A lot of people do that. It's a really terrific idea for helping keep track of things. So what I'm going to do is draw in, first off, the carbon that's the first carbon of my frame of reference. I'm putting a little star on that just to emphasize that that's the carbon there that's at the center. Put my hydrogen that's directly bonded to that, and then that carbon is also directly bonded to a tert-butyl group. So I'm going to go ahead and plug in the tert-butyl group here, and I could have put that up top or off to the left, wherever you want. Doesn't matter, as long as the connections between the atoms are right, we should be able to come up with the correct name for this. So my carbon that was my carbon of the frame of reference, I'm going to go ahead and put a little highlighting on there. That was the first carbon, the carbon in front there. Directly bonded to a hydrogen, directly bonded to a tert-butyl group, and directly bonded to a CH2-CH3 group. So I'm going to go ahead and draw in that CH2-CH3 group as well, and I can draw that wherever I want. I could draw it off to the right. I'm going to draw it up top here and save that spot off to the right for the carbon atom in black that's bonded as the second carbon of the frame of reference. So for now, all of the atoms that we've shown in red in the Newman projection are also shown in red in our redrawn condensed structural formula, and that carbon that's the first frame of reference is shown in yellow. So we're showing the groups that are bonded to that carbon, with the exception of the second carbon of the frame of reference, which we're going to show in black now and plug into our structure. So that carbon that I've shown in black is the second carbon of the frame of reference. I'm going to put a little circle below it to emphasize that that is the carbon that's represented as a circle in our Newman projection. That carbon is directly bonded to two hydrogens, so I'll go ahead and put in CH2. It's also directly bonded to a CH3 group, so we'll go ahead and plug in our CH3 group as well. And now we're left with the task of coming up with the IUPAC name for this molecule. To come up with the IUPAC name, we need to find the longest carbon chain that passes through the molecule. So looking for the longest carbon chain here, trying to come up with where that longest carbon chain is and how long it is. There are multiple options for the longest carbon chain in this molecule. So those multiple options we'll try to trace out here. One of those options is that we do in blue here our 5-carbon chain. That 5-carbon chain in blue would have 3 branches coming off of it. When we have multiple longest carbon chains, we want to go with the one that has the most branches. Another possible alternative is to start here and come through like this. Alternatively, you could have also come up and gone across like so. That would be the same as the other yellow line we highlighted though, because in both cases the last 2 carbons are a CH2, CH3 group. So we'll just highlight that. Another possible option is that you could have started up here and come down and gone through here, but that's also the same as the option that we just drew out. So let's take a look at what we would come up with as the name for this. And as we look at this, it actually becomes apparent that due to the symmetry of this molecule, the line that we've highlighted in blue and the line that we've highlighted in yellow will end up leading us to the same IUPAC name for the molecule one way or the other, due to the fact that there's symmetry here. And so we can choose either of those to be our basis for coming up with the name, because they're both going to lead to exactly the same name one way or the other. So I'm going to go with the blue path that I've sketched through the molecule as my way of going about naming this. Again, you could use the yellow path. you're going to come up with the same name one way or the other due to the symmetry in the molecule. So we start numbering that chain from the end closer to a branch. That's going to put carbon number 1 over here at the far left. Carbon 2, 3, 4, and 5. And we want to specify where the branches are located coming off of that and plug in our parent chain name. So our parent chain name is going to be pentane because it's a 5-carbon chain. Our branches coming off of that is that we're going to have 2 methyl branches there at carbon number 2, and we have an ethyl branch at carbon number 3. Plugging those in alphabetical order, we're going to say that this is 3-ethyl, and then 2,2-dimethyl, pentane as the IUPAC name for this molecule, and that accounts for the carbon chain as well as all the branches coming off. So with that, we'll go on to our next example problem. Our next example problem is going to be to provide the Newman projection for the lowest energy conformer of 4-ethyl 3,5-dimethyl hexane, viewing down the C3 to C4 bond as our frame of reference. So here, we're kind of flipping around the situation relative to the first 2 examples, where rather than being given a Newman projection and predicting a name, instead here we're giving a name and drawing the Newman projection for it. So let's first draw out a line angle formula or condensed structural formula for 4-ethyl 3,5-dimethyl hexane, and then from there we'll convert that into our Newman projection. So hexane, 6-carbon chain. So we need to go ahead and plug in 6 carbons. And I'll go ahead and number those as well. And within that structure, at 4, we need to put an ethyl group in. And at carbon 3 and carbon 5, we put a methyl groups N. And it's going to be the C3 to C4 bond that is our frame of reference for this. So I'm going to go ahead and highlight that. And when we say we're viewing down the C3 to C4 bond, that means that carbon number 3 needs to be the first carbon of our frame of reference. So that's going to be what we represent as the intersection of the lines of that Y shape. And then the second carbon of our frame of reference is carbon number 4, which we're going to represent with that circle that appears in the final structure. So I'm going to put a circle on number 4 there just to help me get myself oriented. And it asks us for the lowest energy conformer of this molecule. And we know that the lowest energy conformer of any molecule has to be a staggered conformation. So what I'm going to do to get myself set up here is I'm going to go ahead and put in a general template for a staggered Newman projection. So I've drawn in the first carbon of the frame of reference and 3 of the groups that's bonded to. And then behind that, I'm drawing my circle to represent the second carbon of the frame of reference. Then I'm going to stagger those bonds so that we have that nice 60-degree dihedral angle separating all the bonds on the carbons in front from the ones in the back. And then we're going to fill this in accordingly. So carbon number 3 is that carbon right here in the center where those 3 black lines come together. And we have to ask ourselves what is going to go onto those 3 black lines at the ends of those lines. And what we'll fill in there are all the groups that are bonded at carbon number 3 other than carbon number 4, because carbon number 4 is represented by the red circle in the back. So at carbon number 3, we have a methyl group directly bonded, and we can plug that into any of these 3 spots. It just has to go to whatever one you want. So we have that methyl group right here. We have an ethyl group, CH2, CH3, so we need to plug that in and make sure you put the CH2 first because that's what's directly bonded to carbon number 3. And then also, to fill the complete octet here, remember that that carbon is actually a CH, and so we need to plug in that H that's directly bonded there. The 4th bond to that carbon is the bond that we're showing in green in our line angle formula. It's the one that goes directly back to reach that carbon that's a big red circle in our Newman projection. So that big red circle represents carbon number 4, and carbon number 4, we have to fill in the lines in red with what carbon number 4 is directly bonded to. Since it's directly bonded to an ethyl group, and it's directly bonded to an isopropyl group. It's also directly bonded to what we're not showing here is the hydrogen. It has to have a hydrogen to have a complete octet. So deciding where to fill in the ethyl group, isopropyl group, and hydrogen is important because we were asked to provide the lowest energy conformer. So that implies that we have to put the bulkiest group that's bonded here at carbon 4 180 degrees from the bulkiest group that was bonded at carbon 3. The bulkiest group bonded to carbon 3, if we look at what we've already drawn here, is definitely that CH2, CH3 group. It has the most atoms. So we need for the bulkiest group bonded at carbon number 4 to go right here, so that it will be 180 degrees away. And that bulkiest group we would expect to be the isopropyl group, because isopropyl group is both more branched and has more carbons than the ethyl group, which is the alternative there. So we'll plug in the isopropyl group, which is CH, and then there's 2 methyl groups there, which you can condense if you want to give parentheses around them, and then subscript 2. Additionally bonded to that carbon is an ethyl group, CH2CH3, and a hydrogen. It doesn't matter which one you fill in where here, hydrogen, CH2CH3. Both of those would be acceptable. So you could have put the CH2CH3 in the upper left and the H in the upper right. That would be totally fine. The main thing here is, since we're asked to draw the lowest energy conformation, we have to have the 2 bulkiest groups. That is the bulkiest group bonded to the carbon that's the back one of the frame of reference, and the carbon bulkiest group bonded to the carbon in the front 180 degrees apart. So it's going to put the isopropyl group that's bonded to the carbon in back in red, and the CH2CH3 group that's bonded to the carbon in front in black, 180 degrees away from one another. So let's solidify that we have this down by doing one additional example problem. This example problem is similar to the previous one, so it's something that you should now be comfortable working out on your own. So it would be a great idea to test yourself by hitting the pause button, determining whether you can do this on your own, and then checking your answer by hitting play again. So provide the Newman projection for the lowest energy conformer of 3,4-diethyl 2,2,5-trimethyl hexane, viewing down the C4 to C5 bond. So let's draw this structure to get things rolling here. We need a 6-carbon chain. So go ahead and draw my 6-carbon chain. At carbon 3 and carbon 4, we need to plug in ethyl groups. So I'm going to number my chain here just so that I can keep track of where I'm putting in my groups. And at carbon number 3, I'm going to go ahead and draw in an ethyl group. At carbon 4, I'm going to draw in an ethyl group because it's 3,4-diethyl. And then at carbon 2, I'm going to draw 2 methyl groups because it's dimethyl at carbon 2. And then at carbon 5 comes in that 3rd methyl group, so we'll go ahead and plug that in. The bond that we're focusing on here, per the directions, is going to be the C4 to C5 bond. So we're going to be focusing on this bond right here within the molecule that connects carbon number 4 to carbon number 5 in this structure. We're going to draw the lowest energy conformer relative to that particular structure. Okay, so let's go ahead and do that. To draw the lowest energy conformer, we need to use our standard staggered diagram. So I put in my carbon that's in front of the frame of reference there in black, and the 3 bonds leading away from it are the bonds to that carbon. And then I'm putting behind that in red, that red circle, to indicate the 2nd carbon of the frame of reference, and the 3 groups bonded directly to that, other than the frame of reference carbon, are going to be shown in red. Okay, so let's go ahead and fill that in now. The carbon in front is carbon number 4, which I'm going to put a little star on here. And in order to fill in those black bonds, we need to fill in the 3 groups that are directly bonded at carbon 4. So that would be our ethyl group right here. It's going to be a hydrogen atom directly bonded there, because that carbon started off with, in our line angle formula, 3 bonds shown to it, and it certainly has to have 4 in total. And then the rest of it's going to be this rather gigantic group. So we need to show each of those groups there, and we'll start, I suppose, with the simplest groups first here. So plug in a hydrogen and plug in your ethyl group, the group shown right there. So CH2 is closest to the carbon that's in the center, because that's what's directly bonded to the carbon in the center, and then CH3, so that takes care of that, takes care of the hydrogens that's directly bonded to this carbon. And now what we need to deal with is the rather large yellow group that's still shown in yellow there in our line angle formula. So in order to do that, we need to draw this out as a condensed structural formula. We could fill it in as a line angle formula here, keeping in mind that this is going to be a carbon right here. That has to be the carbon that's directly bonded to the carbon of our frame of reference. So the carbon of our frame of reference in our line angle formula is shown explicitly as a C right now. I'm going to draw a bond coming over to the next carbon that it's bonded to. That's carbon number 3 of the chain. So the carbon that I'm showing right here is carbon number 3 of our carbon chain. Carbon number 3 of our carbon chain is directly bonded to the tert-butyl group and the ethyl group in yellow. So we need to fill that into our structure here. And in order to do that, there's a couple of different ways. We're going to certainly have to put a branch here because our structure on the left is branched. And we can either fill it in so that we have our carbon directly bonded to one hydrogen, because certainly at this carbon there has to be a hydrogen to fill its octet. Then we could put CH2CH3 to fill in that ethyl group, and we could put up top here or down below as a branch our tert-butyl group. So we have our carbon directly bonded to 3 methyl groups. So CCH33 represents coming up to here to this carbon, CH3, CH3, CH3. So that's representing the tert-butyl group that we have showing over in our Newman projection. And then the ethyl group bonded to that carbon number 3 is shown right here, CH2 and CH3. So that fills in the groups that are bonded to that carbon. All right, next up, we need to fill in what's directly bonded to carbon 5, because carbon 5 was the second carbon atom of our frame of reference. So I'm going to put a red circle around that carbon number 5 for emphasis, because that's what's represented by a red circle in our structure over here. That carbon number 5 is directly bonded to 2 methyl groups, and it has to directly be bonded to a hydrogen as well. So to make the lowest energy conformer here, which we're asked to do in the problem, we have 2 identical groups here, 2 methyl groups. So in order to make the lowest energy conformer, what we need to make sure that we're doing is putting that one of those 2 CH3 groups 180 degrees away from the bulkiest group that is in front. So the bulkiest group that was present in front was this gigantic group, and so therefore we need to put one of those 2 methyl groups from the carbon and back 180 degrees away from that, and that's exactly what we're going to do. We're going to plug in CH3 right here. And then the other CH3 group, since the other CH3 group is the second bulkiest group here, we're going to plug in right here, because that's going to put that CH3 group next to the least bulky group that's bonded to the carbon in front, that is the hydrogen atom in black there. And then finally, we're going to put in the hydrogen right here. If we'd instead put this CH3 group that is in the upper right position down here at the bottom, that would have put that CH3 group between 2 bulky groups and therefore have raised the energy of the system. So it's better to have the bulkiest group spread as far apart as possible. Certainly the way to set yourself up initially to do this is to put the bulkiest group that's on the carbon in front, that's the one in green, separated by 180 degrees from the bulkiest group in the carbon on the carbon that's in back, which was a methyl group here. But then there was also a second methyl group there that we had to think about where to put that second methyl group, the one in the upper right corner that I'm highlighting right now. And that we wanted to put in the least crowded environment possible. And it's going to be less crowded for it to be sandwiched between a hydrogen and that gigantic group in green than it is to be down at the 6 o'clock position, where it would be between an ethyl group and that gigantic group. So with that, we minimize the amount of torsional strain in this molecule. Torsional strain being the crowding of the atoms and the crowding of the bonds. We've staggered the bonds to minimize the torsional strain. We've also spread the atoms out as much as possible here. So with that, hopefully you have a better understanding of drawing Newman projections, converting names into Newmans, and things like that, which is one of the central skills of organic chemistry.